Today we're going to talk about the different reaction types that we have to know. Now what I'm going to do is I'm going to combine both the organic types of reactions that we need and then the inorganic types that we're going to need to know into one, because there's a lot of overlap and we might as well do them all at once. So for addition, combination, or synthesis, this is going to be I'm going to break this down into two types. There's organic addition, combination, or synthesis. Notice I can use the same word for each, meaning addition is the best word to use because it explains exactly what's happening. Combination or synthesis also means the same thing. Now for organic addition, we need a double bond. That is a requirement. So it could be a double, it could be a triple. It doesn't make a difference. And only one product is formed. So the first one is filled in for us. So take a look at what happens. So the bond between the two H's breaks and one of the bonds between the two C's break. And so that allows one H to attach to one C and the other H to attach to the other. And the reason being, we know the carbons need 4 bonds. And so since they lost one each, they're going to need one each as to make a stable molecule, and that's where the H's come in. And that's basically it. So if we did the same thing for these, you're going to see the bond between the H and Cl is going to break, and the bond between the two C's are going to break, and then the H goes to one, and the Cl goes to the other. So you end up with this. So there is your product. So notice the thing they have in common: you start with 2, you end with 1. You start with 2 reactants, you end with 1 product. I'm going to do the next 2 as well. So for these guys, it's H2O, so it doesn't matter how you break it. You're going to break it up into an H and an OH, and then you're going to break the bond between the C's, and then down here we break the bond between the BRs, and then we break the bond between the C's. One H goes to one carbon, the OH goes to the other, and in this case a BR goes to one carbon and a BR goes to the other. So you end up with this. Now, with these, a common question I get a lot is, does it matter which one the O goes to the OH and which one gets the H? For molecules that are small like this, it doesn't, because whether you put it here or put it here, you just take the molecule and flip it, and it's the same molecule. So that's not going to matter. When the molecules, and then for this bigger molecule, it would actually matter because we would get different products depending on what happens. But because this molecule is perfectly symmetrical and it's 2 BRs either way, it's not going to matter for this one. So you put 4 in a row. Now notice for this last one, I didn't write the H's in. I just didn't, you don't have to at this point. But I did put the BRs both down. It does not matter if you put them both up, down, doesn't make a difference. They're free to rotate around the molecule. Now, there are instances where you end up making more than one product, because half the time, let's say the OH, in this example, the OH will go to one carbon and the H will go to the other, and then the other half the time they'll flip, and so you end up making 2 products. Half of them are this way and then half of them are flipped. On a small molecule, it doesn't matter. On an asymmetrical molecule, it might. Here's what I'm going to tell you: you're never going to have to worry about that. As long as you know, break the bond and add them to it. They typically, what the regents will do is, if there's more than one potential answer, they accept both potential answers, because trying to figure out which one is the right one or which one comes out more often is is bare minimum a college level organic chemistry problem. And so we're not going to worry about that type of stuff. We just need to know, mush them together, break the single or break the double bond, or if there's a triple bond, you break one of the 3 bonds and drop it down to a double bond. For non-organic or inorganic addition, same idea. You combined 2 or more reactants to make a single product. Now, you don't have to worry about this as much. You just have to be able to identify it. Don't worry about these blank spaces here. That's for a topic that we're going to learn in a little bit called balancing chemical equations. I'm not going to get into it, but basically, here's how you do inorganic addition. You look at it and you say, okay, 2 things, they came together. There were 2 here, they came together. There were 3 here, they all came together. That means it's called addition or combination. Those names should be very obvious. Synthesis is a little bit less. Don't worry about the fact that there's 3 Mgs here and there's only 1 here, and there's or 2 Cls here and only 1 here. That's what balancing actually fixes. But again, we don't worry about that. We're just looking at the general trend. Is it coming together or is it breaking apart? The next one we're going to do, here's some more inorganic addition. They're pretty simple. 2 becomes 1, 2 becomes 1, 2 becomes 1. You get the idea. Now, if you notice, more than one different, here I have S and O2, and they make SO2, and here I have S and O2, and they make SO3. Same thing with the FEs and Os. More than one product is possible, but again, we don't really care about that because it doesn't really matter. It's we just need to know if it's addition or not, and that's pretty much it. Now, substitution is our next one. If you think about the name substitution, think about what's happening in a sports game. When they substitute a player for another, what are they doing? Well, they're trading one player for another player, okay? And so one element replaces or trades with another, and you can get more than, you often get more than one product form. Well, you're always gonna get more than one product form, as a matter of fact. So in this case, let's take a look. This H traded places with one of the BRs to make this. Done. Does it matter which H I picked? No, not really. Not at this level. It's not going to make a difference. So you could swap it with this H, this one. Any of the H's were fair game. You just trade them. And that's why it's called substitution. So for you to do one, I'm just going to do the easiest thing. I'm going to switch the H with the nearest CL. And I'm going to end up with this. Done. That's all substitution is. And for the last one, fermentation, we're not going to really draw these out. Fermentation is kind of a memorization one. So fermentation is making alcohol, and your products are always going to be carbon dioxide and alcohol. That's really it. So the alcohol could be anything. The most common, this doesn't have to be this way, but the most common alcohol that we make is ethanol, which is this one. Eth meaning 2 carbons in a row, and then the OL tells me it's an alcohol, so this is ethanol. It does not matter where you put your H or the OH group because it's such a small carbon chain. It doesn't need a number, so that's no big deal. And CO2 is just CO2. And then the sugar is our basic sugar, C6H12O6, but it doesn't have to be glucose. It could be any of the sugars. You know, if you remember from biology, you learned a bunch of different sugars, but glucose is definitely the most common because we're not really, this is a chemistry course. We're not really testing, do you know all the different sugars? We're really asking, can you recognize that this reaction is called fermentation? And so fermentation is really, you take a sugar, you make alcohol and CO2. It's that simple. That's all you need. You can put in the yeast part because we used yeast bacteria to do that when we do this pretty much all the time, but you don't need yeast bacteria. You can actually, there's other ways to do it using more advanced chemical methods. Yeast is the easiest, which is why that's what we do on a general scale, but you can do it other ways with like temperature and pressure and things like that. But those are the first 3. I'm going to break this video up into multiple segments so it's not too long. In this section, we're going to do combustion and decomposition. So combustion is pretty simple. It is when you add oxygen to something. That is a requirement. It's non-negotiable. It is, when we talk about combustion, a lot of people think of fire, right? It's burning of fossil fuels or hydrocarbons. That's what your cars do. That's why the engine in most cars, unless it's an electric car nowadays, is called a combustion engine because it burns fuel to make a fire, to make the pistons move and, make the car go. So that's the general idea. Your products are carbon dioxide and water. That's always going to be, well, not always true, believe it or not, but that is almost always true. So let's just make this more accurate. I guess often is a better word. Light and heat are a product, although we don't always see it. And another name for combustion is oxidation. So it could be called either one. So combustion for organic compounds is simple. You take any organic compound, so this is typically a hydrocarbon, okay? So this is your hydrocarbon right here. Don't worry about the 2 in front, that's balancing. So again, we're not too worried about that. But it's C8H18. You add oxygen. Again, I'm not worried about the 25 in front, that's a balancing issue. So you take a hydrocarbon, you add oxygen, and look what you get. CO2, H2O, and energy. So that's organic combustion. This part, the actual hydrocarbon, it could be anything. It could be C8H16, it could be C2H4, C2H6, C2H8. Doesn't matter if that exists, it doesn't make a difference. Some hydrocarbons, so carbon-hydrogen combination, that's what a hydrocarbon is, add oxygen, you get CO2, H2O, and energy. The energy part doesn't even really need to be there because it's so common that a lot of people just assume this part and they don't even write it in sometimes. All right, so that is organic combustion. So if you look, here's another one. This is a hydrocarbon. You get oxygen, you add oxygen, you make CO2 and H2O. I didn't include the energy here. It doesn't have to be there to be combustion. Here's a different organic combustion one, C3H8, but if you notice, this part's the same. Oxygen, you add oxygen, you get H2O and CO2. These two are inorganic combustion. So these still count as combustion, although a lot of times scientists would be more likely to call this oxidation, although oxidation and combustion, you can really lump them together. So if you notice here, I'm adding oxygen, but there is no CO2 and H2O byproduct. Instead, I'm actually combining the S and the O. Here I'm combining the Mg and the O. So this does count as combustion, although most people would call it oxidation. Most scientists would call this oxidation, even though combustion is a synonym. All right, and these also count as combination, addition, or synthesis. And the reason is because we're adding two elements together to make one, adding two together to make one. So it turns out some chemical reactions do fall into more than one category. The last one that we're going to do on this page is decomposition. Decomposition, just like biology, decomposers, they break things down. So a decomposition reaction is going to be a reaction that breaks down a compound into its individual elements. So here, MgNO3 twice gets broken down into individual Mg, individual N, even though there's two, it's still an element, so it counts, and individual O. Even though there's two there, it still counts. These two are part of Brinkelhoff. Hg and O gets separated into Hg and O individually. The effect, again, the O2 doesn't matter. H2O can be separated into elemental hydrogen is a better way of saying it, and elemental oxygen. That's their element forms. So that's decomposition, and that's everything on this page. In this video, we're going to go over esterification and saponification. Saponification will carry us on to the next page, but we'll start with esters. Esterification, if you remember, we did a lab on this, or I shouldn't say this, you will do a lab on this right after this, so this is going to be really good notes to have because this is exactly what you're going to be doing in the lab. So esterification is what it sounds like. You're making something into an ester. Esters typically smell nice, but they don't always have to, but they do typically have smell. Whether you consider it good or bad is a personal preference. So the way you make a ester is by adding an organic acid and an alcohol and mixing them together. Now, you haven't learned this about acids, but acids like to give off their H pluses. They give off NH plus is a better way of saying it. And specifically, and again, we will learn this, that in an organic acid, the H attached to the OH, the part that looks like an alcohol, that H is going to come off, okay, as an H plus. And that H is actually going to react with the alcohol from the alcohol, and that is going to come off to make water, because when you add an H and an OH together, you make water. Now, that leaves this carbon with not enough bonds, and it leaves this oxygen with not enough bonds. So what happens is the oxygen and the carbon bond together, and that is, that's this bond right here. I'll use yellow because it's a little bit better. So that's this bond right there. All right, and that's how it works. So for these two practice problems, you're going to do the same thing. The H and the OH come off and make water, and then we take what's left over and link them together. Now, if you happen to get it wrong and you accidentally did the OH from the alcohol and the H from the, or the OH from the organic acid and the H from the alcohol, it's ultimately not going to make a difference. But if they ask you to circle which ones come off, if it were a Regents question, I have seen this, and they said circle the ones that are going to come off to make the bond, then you need to circle the H from the organic acid and the OH from the alcohol. But if it was just draw the products, then they're not going to know. And even if you circled them on the Regents and you happen to get it wrong, like if you accidentally circled the wrong pair, if that wasn't part of the question, I don't think anyone would care either. I personally wouldn't, because I'm only going to look at the answer. So what do we get? And so those are your esters. The hard part about esters is going to be naming them, although that's not in this lesson. You should know how to name them already, but drawing it out is really not that bad. You just have to know this is what happens, and I have actually seen this question show up on Regents. So saponification, well, everyone says it's saponification. I like to say soaponification, and the reason is because saponification is making soap. So when you make soap, it's pretty easy. You take a fat, you add a base, which is, again, a chemical that we haven't learned about yet, but it's similar to an acid. So you've probably heard of the word base as acids and bases. So you've definitely heard of that. So we take a fat, we add a base, we get a glycerol. Again, you don't need to know what that is. It just looks like this. And then we make a soap. So the easiest way to identify saponification is it uses this big, giant E-shaped molecule. And if you look, it's even bigger because see the CH2 with a 6 outside? That means there's 6 repeating CH2s along this chain. And then you make this even bigger molecule where you pretty much take them all and lump them together and you get this giant chain. Okay, and that's what saponification is. You would never have to draw this. But you may have to answer questions about like which reaction is saponification and what makes a soap a good soap. And that actually leads us to our next topic. So not our next topic, but our continuation of this one. So down up here, I have draw a soap molecule. So to draw a soap molecule out, let's take a look. We start with a CH3 and then it's going to need 16 CH2s. Then it gets an O, an O, and I don't even have space, an Na plus in brackets at the end. Normally this thing is put in brackets like that. Okay, so that's your soap molecule. I am not writing out all the hydrogens for this. I'm just going to put the lines. Okay, and the reason the soap molecule is so gigantic is because of two things. There's a saying that we like to use, and you're going to learn more about this, but it's called like dissolves like. And it's used with the saying that you already know, SNAP, symmetrical, nonpolar, asymmetrical, polar. And what it means is this: polar molecules like to dissolve in other polar molecules. This is actually the answer to why oil and water don't dissolve. Polar molecules like to dissolve in other polar molecules. Nonpolar molecules like to dissolve in nonpolar molecules. We will explain the whys when we get to the actual unit where we learn this officially. I'm just kind of giving you a brief introduction. And the reason oil and water don't dissolve is because water's polar and oil's not. All right, and so if you ever look at salad dressing with like the layering, that's why they never dissolve into each other and they always end up separating, is because they have different polarities. Well, what makes a good soap is that it washes off everything. It'll take off oils, it'll take off water-based stains. So normally you don't really need a soap to clean off something that's soluble in water, even though we use it anyway. But soap, what makes a good soap is that it can do everything. It can dissolve polar things because it has a polar end. It can dissolve non-polar things because it has a non-polar end. And the question would be, well, how would a molecule be both polar and non-polar, right? It's usually you're asymmetrical and you're polar, or you're symmetrical and you're non-polar, right? That's normally the way it works. Well, there's a different issue going on with the soap molecule. The soap molecule is so long, it would be like if you had a house that was so outrageously big that someone could be over here having a house party, right? And you could be all the way on this end of the house and not even know what was going on because the other end is just so ridiculously far away. Now, most people don't have that scenario, but that's what happens in a soap. On this end of the molecule, if we look, it is symmetrical and therefore non-polar, okay? And then this end of the molecule is so far away from the other side that it almost resets the symmetry. And now we can actually do it again on this end. And if you look, you could say, well, in this case, with this double bonded O and this O and Na on this side, this end is symmetrical, and therefore polar. And because the molecule is so long, it can actually do both at the same time. And that's what makes something a good soap. If you get something that's oil-based on you, right? Like oil, like you're cooking and you get grease on you or something like that, well, this end of the soap molecule is going to take care of that and try to dissolve it. If you get something that's salt-based or water-based on you, well, this end of the molecule is going to be able to dissolve that. So that is what makes something a very good soap. Now we're going to talk about polymerization. So polymerization, if you've ever watched Yu-Gi-Oh!, it is the same thing. It is literally taking small individual molecules and linking them together to form larger, bigger molecules. Now, obviously, in the cartoons and in anime and things like that, they usually merge themselves into a larger, stronger, different thing. In chemistry, it's not so exciting. We basically take little individual chains that we call single units or monomers, mono meaning one, and we form them or link them up to make a polymer, poly meaning many. Okay, and there's two types of polymers. There's natural polymers, like the types that we find in nature, so proteins like in your muscles, starches like carbohydrates, and cellulose like wood are what are natural polymers, and they're part of the reason our muscles are so as strong as they are, and they're also the reason carbs are usually can store as much energy as they do, and the same reason that trees or wood can be as strong as it is. Okay, and so those are natural polymers. Synthetic polymers are things like plastic, nylon, vinyl, or Kevlar. These are all made from oil-based, well, nowadays there's multiple options, but typically these are made from oil-based products like gasoline. Well, not gasoline, but the actual material that gasoline comes from, we're going to call it petroleum. It's typically made from that. And synthetic polymers are also very light and very strong. If you compare a, plastic bag for a paper bag, the amount of weight that the bags can carry before they rip compared to the amount of weight that the bag itself weighs, the plastic bags, I know we ban them, but the plastic bags are much stronger per weight unit than the paper ones, or at least the paper ones that are around now. Maybe they'll make better paper bags, but I don't know if they'll be as light as a plastic bag and still be able to hold as much. But those are our two types of polymers. Now, what do we do and how do we draw it? It's real simple. For polymerization, you're basically going to do two types. There is condensation polymerization, and if you know what the word condensation means, right? Condensation, if you ever see it, like when you take a shower, the fog that builds up on the mirrors and the glass, that's called condensation, and that's water. So condensation polymerization is where we remove water. So just like the esterification reactions, we do the exact same thing. We take the H from one, in this case it's an N, we take the OH from the other end and we remove a water. And then what's left over bonds together. So this thing would look like this. Now, I didn't draw out all my H's. I can go in and fill them in. I was just trying to keep it the same format as I did on the left side to make it a little bit easier to view it, but that's it. Now, this does not count as a polymer, okay? This is barely, most people would not count this as a polymer. This is just merging two monomers together. To be a real true polymer, you need to do this like 20, 30, 50, 100, several hundred, several thousand times. So you're gonna have to make a much bigger molecule than this. And so that actually will lead us to, how do we draw polymers? Because if they're that big, they're gonna take all day to draw. And I'll get back to that in a second. And then the last type of polymerization is addition polymerization, which if you remember organic addition, and if you don't, you can go back and watch that. Well, it's the same thing. It's just organic addition on a large scale. We take one of the two bonds, or if you had triples, it would be one of the three bonds. We break them, and then we link together the things that are a bond short. Now, in this example, there would need to be more of them because I'd have to now link this together with something, and I'd want to link this together with something, and you'd go out bigger, but I only drew 3, so we're just going to go with that. And so it's going to look like this. And if we drew it the way Table R would draw this, right, using their format, it would look like this. It would say these two would go out to more carbons and would be of varying lengths. If I said R and R, that would imply that the chain on the right side would have to be the exact same length as the chain on the left side. So by saying R and R prime, or R1, whatever you want to call it, that's telling you that this chain could be, 500 carbons long and this chain could be 2 carbons long. It doesn't mean they don't have to be the same length. And so that's the way it would look like if it were table drawn based on table R. And now, how do you draw them? How do you shorthand and draw these molecules? It's simple. You take the repeating pattern, the pattern that repeats most frequently, right? Or the smallest repeating pattern you can find. In this bottom case, it's this, and in the top case, it's this, right? And then you just put an N outside, and the N is the number of times it repeats. So that's how you do polymers. So you would take their monomer form, right, or the smallest repeating unit that you have. In this case, it's a little larger. And then you would just write a number outside. That number could be 10, it could be 100, it could be thousands. And that's the way you don't have, so that way you don't have to write the whole thing out, because it would literally take all day. So that is polymerization. In this last video for our organic and non-organic reaction types, we have 2 inorganic reactions. So these are reactions that don't involve mainly carbon and hydrogen. There might be carbon in them, but they're not what we would call organic reactions. So we have single replacement and double replacement. They sound very similar. And the reason they sound similar is because they look very similar. But it turns out, we will learn later on in the year, they're nothing alike, meaning what drives these 2 reactions to happen is totally different principles within chemistry. So we're going to learn about them at different times of the year. Single replacement we'll learn first, and double replacement we will learn, double replacement we'll learn first, and single replacement will be like the last thing we learn for the entire year, because they're actually pretty complicated as far as what causes them to happen. But for now, we'll just learn to identify them. So here's my example. So I have element A, element B, element C. So these are different elements. And the way you identify a single replacement reaction is an element and part of a compound trade places. So I like to call it element compound swap. So I take the element A in this case because it's alone, and the compound B because it's part of a compound. It's with C, that's what makes it part of a compound, and they trade. Does it have to be A and B that trade? No, A and C can trade as well. It doesn't really matter. As long as you have an element trading places with a compound, you end up getting a new element and a new compound. So the example would be B alone is a new element because here it was part of a compound, and now AC is a new compound because it's different from BC. So here, take a look. We have Zn trading places with the copper. So you end up with copper alone, now it's an element, it was in a compound, and the zinc was an element, it's now in a compound. So element, compound, swap. Bromine and iodine trade places. Now you don't have to worry about the fact that it's Br2 here, and then it's only Br here. That has to do with, when you form ionic compounds, they come together in different ratios, and then we use balancing, which you haven't learned yet, to take care of the fact that they're unequal. Again, we're going to learn it very soon, so it shouldn't be too big of a deal. But all you need to say is, all right, this is an element. This is a compound. Part of this element is trading places with part of this compound to make a new compound, Na with Br, and a new element, I alone. Done. In this one, K trades places with one of the H's. So that still counts because now K was an element, it's now in a compound as KOH, and H was in a compound, and now we have H outside the compound. Now granted, H is still in the compound here, but we also have elemental H, which is what's important there. So that's how you figure out if something's single replacement. At this point, you will not have to figure out the products. You're just going to have to identify the reaction for now. And then double replacement, I like to call this one compound swap. In other words, I take 2 compounds and they swap their positive ions. Or you could word it and say, well, they're going to swap their negative ions. It doesn't matter how you say it. You end up with the same result. Meaning Na is a metal. It's going to be the positive thing in the reaction. If you didn't know that, you should know how to assign oxidation numbers. If you don't know that, go back and watch my video. But you're going to basically trade places with the H, and the Na comes out. And so what do you get? The H is now with Cn, right? Because this is the polyatomic. And the Na is now with SO4 because SO4, again, is a polyatomic. You don't need the parentheses around it. I'm just writing it in so you can see the polyatomics to make them a little bit easier. But the sodium and the H swap. For this next one, this is a polyatomic. NO3, obviously, S is an element, but sodium is going to trade places with CD. And so sodium is a metal. It's now going to be with NO3, and NO3 was the metal here. It's now going to be with S. So you may not get the same amount of each, but you do get new compounds being formed, and that's what's important. And then the last one, calcium is going to trade places with hydrogen in this case to make H with OH, otherwise known as H2O. That's what it would look like, but we're never going to write it that way. That's why it changes form. And then calcium is now going to be with chlorine. So these are double replacement reactions. Basically, the one element in the compound trades with the other element of similar charge. In other words, you could say the positive ions, which are typically the metals, they can swap. Or you could say that the negative ions swap. I like to do the positives because they're always written first, so it just makes things easier. But you could view it as the metal swapping. It wouldn't necessarily be wrong. It would just be a little bit more work. So that is all the reaction types, both organic and inorganic, that we have to know about for chemistry this entire year.